Now I'm going to talk about famous theorem, which is Jordan's lemma. In the evaluation of integrals of the type just we look at in section 80, it is sometimes necessary to use Jordan's lemma, which is stated here. Okay, here let's start by looking at this figure for Jordan's lemma. We have our complex plane with the real axis here and the imaginary axis y. We've also got a smaller circle with a radius r naught here that's centered at the origin, and we've got a larger semicircle with radius r that's also centered at the origin. Here capital R is greater than capital R naught. I'm going to label the semicircle as G sub capital R. Oh, sorry, this figure. Okay. Sometimes I'm going to use some different name here for this figure. Theorem says, suppose that three conditions. The first is a function f of g is analytic at all points in the upper hyperplane, which can be described by this: y is greater than or equal to 0, that are exterior to a circle given by absolute value of g is equal to capital R naught. And the second condition is C sub R denotes a semicircle described by g is equal to capital R times e to the I zeta. Here zeta is from 0 to pi, where R is greater than R naught, as we said in figure 103. And the final condition is that for all points G on the arc CR, there is a positive constant capital M sub R, M sub capital R, such that the absolute value of f of g is less than or equal to capital M sub large R. And as capital R goes to infinity, the limit of M sub capital R is equal to 0. Then, for every positive constant A, we have this result. Limit as R goes to infinity, integral along to CR, fg e to the IAG dg is equal to 0. If all these statements apply, then Jordan numbers says that contour integral of f of g times exponential of IAG over the semicircle CR in the anti-clockwise direction approaches 0. As capital R approaches infinity. Here A is a positive constant. Next, we are gonna prove this lemma. The proof is based on the Jordan's inequality. It does not seem very related to Jordan's lemma. What I'm saying is Jordan's inequality, but it will come together at the end. We are gonna start by graphing two functions on the Cartesian plane. Y equals to sine theta and y equals 2 theta over pi. 2 theta over pi is just a straight line going through the origin here. You can see the figure here. That becomes 1 at theta over 2. Okay, if we input this pi over 2 here for the theta, then we get this 1. So this value is 1. Just like how sine theta becomes 1 as theta equals pi by 2. Okay, we insert this with pi over 2, then we get 1 for the value of sine theta. Now we can see from this graph that sine theta is actually greater than or equal to 2 theta. This graph is greater than or equal to this graph. What I mean is line between 0 and pi over 2. This is actually important because it means that negative exponential of capital R times sine theta is less than or equal to the negative exponential of capital R times 2 theta over pi, where capital R is obviously a positive constant, which it is because it is the radius of the semicircle. And since the exponential of negative capital R here negative capital R sine theta is less than the exponential of negative to capital R times theta over pi I. That means the integrals of these quantities from 0 to pi also follow the same inequality order. Now you can actually compute this latter integral. We're going to prove this Jordan's inequality first. Okay. Here. Here we can compute this integral, and when you do that, you will get pi over 2 times capital R times 1 minus exponential of negative R. Here, capital R is greater than 0. Hence, since capital R is greater than 0 here, we can say that this quantity is also less than pi over 2 times capital R, because the exponential of a negative number here is positive number that is less than 1. Okay, so this will be greater than this. Here, because if we take 1 minus of that and multiply by pi over 2 times R, we end up with something that is in fact less than pi over 2 times R. So, therefore, the integral from 0 to pi over 2 of exponential of negative capital R sine theta is less than or equal to pi over 2 times capital R. Here, capital R is greater than 0. So, let's go back and look at the graph of sine theta. You can see that sine theta is symmetric with this axis when we reflect it about theta equals pi over 2. So what we can say that is integral from 0 to pi of exponential of negative capital R sine theta is twice the integral from 0 to pi over 2. What I mean this, with the same function this. Therefore, integral from 0 to pi would then be less than or equal to pi. For this, we need double. So we consider this quantity here for this. Then 2 times 2 capital R pi over 2 times capital R. So we cancel 2, then we get this pi over capital R.